Hello, everyone. Welcome to the Magnetosphere seminar series. I'm Nitin Shivadas from Boston University, and I'm going to be your host for today. If this is the first seminar in this series that you're attending, I'd like to mention that as the seminar is going on, please turn off your mic and video. If you have any questions to the speaker, please type it in the Zoom chat, or for people who are viewing this from the YouTube stream, please send in your questions through the Contact Us form on the website link provided on the description below on the stream. I'll bring up your questions one by one after the end of the talk to the speaker. So it is my pleasure today to introduce to you my good friend, Ying Zou. Ying Zou is an assistant professor at the University of Alabama in Huntsville. Her research interests focus on the interaction of the solar wind with the Earth's magnetosphere and the coupling between the Earth's magnetosphere, ionosphere, and thermosphere. She has studied magnetopause reconnection, ionospheric convection, as well as thermospheric dynamics through a combination of spacecraft and ground-based observations. She received her Bachelor of Science from Peking University in 2010 and PhD from UCLA in 2015. After graduation, she worked as a postdoc at UCLA, a research scientist at Boston University, and was also awarded the prestigious NASA Jack Eddy Fellowship to work at Boston University. In 2019, she joined the Space Science Department at the University of Alabama in Huntsville. So today, she will give us an overview of the magnetopause. So Ying, feel free to start when you're ready.
Okay, let me share my screen. Okay, thanks Nathan for the great introduction. It feels different in a good way to have a close friend and also former office mate introducing me. Before the start of this presentation, I would like to give a big shout out to Kyle for the great organization of this seminar series. I have attended every seminar and have benefited and enjoyed a lot. And actually this seminar series have become my new routine to kick off a new week of work. Okay, back to the presentation. Today's topic is the magnetopause. And as we already know, the Earth's intrinsic dipole field, here's my cursor, is separated from the ambient magnetosheath by a thin current-carrying surface layer. And this surface layer is the magnetopause. Because the solar wind mass and momentum entering the magnetosphere should all cross this magnetopause, this boundary is the subject of intense research. Here, I'm just giving an example of how the magnetopause looks like in spacecraft data. The data were taken not long ago, and the figures come from the MMS website. To identify the magnetopause, a common criterion is that the magnetic field should show a change in its direction. And this criterion is good for identifying magnetopause with a large magnetic shear, such as during southward IMF. For northward IMF, the field rotation can be small, and therefore plasma data are also used for identification. For this specific figure, the ion energy changes from a few hundred eV in the magnetosheath to more than 10 keV in the magnetosphere. For the electrons, their energy change from several tens of eV to several keV. There's a drastic decrease in the plasma density because magnetosheath is much denser than the magnetosphere unless there's a plume. And the following panel showed the spacecraft potential, which can also be used to infer the plasma density. For this specific magnetopause crossing, we see there's a fast ion Bach flow that was flowing southward. And as we will see later on, this actually is a signature of magnetic reconnection. In this presentation, I will discuss the magnetopause from two perspectives. One is the structure, the other is the dynamics. For the structure, I will talk about the location and shape, the magnetopause motion, its thickness, its electric current. For dynamics, I will talk about magnetic reconnection and Kelvin-Helmholtz instability. Okay, the location and shape. From textbooks, the location and shape of the magnetopause is determined by the dynamic pressure and the thermal pressure of the solar wind and the magnetic pressure of the magnetosphere. This quantitative relation allows us to construct a model of the magnetopause that is driven by the solar wind. One of the most widely used model is the Zou model. In this model, the magnetopause is assumed to be cylindrically symmetric, and the shape of the magnetopause is described by this functional form. Here, r is the radial distance from the Earth's center, and theta is the angle between the vector r and the Sun-Earth line. There are two parameters in this functional form, which are r0 and alpha, which represent the standoff distance at the subsolar point and the level of tail flaring, respectively. These two parameters are functions of the solar wind parameters. For example, here, dP represents the dynamic pressure of the solar wind, and Bz is just the Bz component of IMF. So once the solar wind condition is known, the functional form of the magnetopause is known. The right just showed the modeled magnetopause. The top panel shows the magnetopause under a fixed dynamic pressure, but different Bz. When IMF is southward, for example, this solid line, the magnetopause, the dayside magnetopause moves earthward, and the tail flaring increases. This is caused by reconnection at the dayside, which removes magnetic flux and transport them to the night side magnetotail. And the bottom panel shows the magnetopause under a fixed Bz, but different dynamic pressure. The bigger the dynamic pressure, the more compressed the magnetopause is. While the Zou model is a handy tool, and I highly recommend you to use it, the model does have limitations. It only characterizes the global shape and location of the magnetopause, whereas in reality, the magnetopause contains localized structures. These structures can arise from Kelvin-Helmholtz instability, hot flow anomalies, fast magnetosheath jets, and so on. For example, the hot flow anomalies, as we learned from previous speakers, can decrease the pressure in the magnetosheath and hence allow the magnetopause to bulge outward. And an example is presented on the right. This figure shows the magnetopause, the bow shock, and the solar wind in this XY plane. The dotted line gives the modeled magnetopause, which is the Zou modeled magnetopause, and the solid line here is the measured or the observed magnetopause. And we can see that the observed magnetopause is deformed relative to the modeled magnetopause, and this bulge here actually propagates to the minus y direction. The color-coded background in the magnetosheath is the total pressure measured by spacecraft. And the reason for the magnetopause to bulge outward is this low pressure region colored in blue according to this color scale. And this low pressure region is ultimately driven by the hot flow anomaly at the bow shock. And also at this low pressure region, the plasma flows were directed sunward, as shown by these arrows, and this is consistent with the protrusion of the magnetopause. Besides the shoe model, more sophisticated models have been developed to account for the details of the magnetopause. For example, the cylindrical asymmetry and the indentations near the cusp, the dependence on solar wind parameters other than the dynamic pressure and BZ. But unfortunately, the performance of none of these models is perfect, which is expected from the nature of statistical model. And here just shows the histogram, which display the radial distance between the modeled magnetopause and the observations. Positive values means the model overestimates the radial distance of the magnetopause, and the negative values means underestimate. For the shoe model, the median difference is about 1.48 Earth radius, which is positive, and that means the modeled location is further out from the Earth than the reality. Therefore, although the magnetopause seems to be a simple boundary, surprisingly, we cannot even reliably predict its location and shape at a given instance of time. This situation hopefully can be improved by the upcoming SMILE mission, which can provide images or snapshots of the magnetopause for various solar wind conditions. Now, if we add the time dimension into those 2D drawings of the magnetopause, as if watching the movie, the magnetopause is constantly moving. The motion can be attributed to time-varying solar wind and magnetosheath conditions, waves and instabilities at the magnetopause, which includes Kelvin-Helmholtz instability and reconnection-related phenomenon. Observationally, the motion can be directly determined with spacecraft constellations. For example, when the spacecraft crosses the magnetopause successfully in time, we can compute the motion velocity from the time differences between crossings and the relative positions of the spacecraft. And here I'm presenting the results of 3 studies using 3 different space missions. All of them are histograms showing the number of events at various magnetopause velocities. The velocity ranges from several to more than 100 kilometers per second, as shown in all these 3 figures, with an average of a few tenths of kilometer per second. In comparison, the spacecraft velocity, the orbital velocity, is often just 1 to 2 kilometers per second, which is negligibly small compared with the magnetopause motion. Note that it is also possible to infer to use only single spacecraft to infer the motion, although in this case, strong assumptions need to be made during the data processing, but the results look quite similar to here. Now, the thickness of the magnetopause. In ideal MHD, the thickness of any discontinuity vanishes, whereas kinetic models predict that magnetopause thickness should be on the order of 1 ion gyroradius. Interestingly, neither of the 2 descriptions are correct. The thickness can be computed as the magnetopause motion speed along the normal direction times the duration of spacecraft crossing. And in this Boucham and Russell's paper, the thickness is found to vary from 200 kilometer to 1,800 kilometer, with an average about 800 kilometer. And this is about 10 ion gyroradius. The thickness depends on the magnetic latitude, and it is thinnest at the equator. The thickness also depends on the local time. It is generally thinner on the day side than at the flanks. If you look at this figure carefully, you may notice that the thickness is thinner at dusk than at dawn. And this dawn-dusk asymmetry is interesting and actually is still not well understood. It could be due to different magnetosheath conditions, different occurrence of magnetopause waves, or different current structures, and so on. It is also worth mentioning that studies have also explored the thickness on dependence of thickness on several other factors, such as IMF and the geomagnetic activity. And so far, it seems that only plasma beta is closely controlling the thickness. So in fact, what controls the thickness is still an open question awaits to be answered. Since the magnetopause is a current layer, how can we not talk about the current? The current is what is required from the Ampere's law to bring the change in the magnetic field across the magnetopause. But what is the nature of this current? Chapman and Ferraro treats the current as flowing between plasma with no magnetic field on the solar wind side and magnetic field with little or no plasma on the magnetosphere side. So as particles enter the magnetopause, they will be turned around by the Lorentz force and ejected in half a gyro period. Recent MMS observations suggest that ion diamagnetic drift may be a more description of the current than the Chapman-Ferraro model. And if you forget what the ion or the diamagnetic drift current is, this little insert can help you. But briefly speaking, it arises from the pressure gradient across the magnetopause. The top panel shows the magnetic field vector measured by MMS, and such a magnetic field rotation here is associated with a current, which is this black line in the second panel. There are two other curves in the second panel, which is this red curve, that's the diamagnetic current, and the green curve, that's the curvature drift current. And the high degree of similarity between the black and red indicates that the current, the magnetopause current, is mostly contributed by the diamagnetic current. In the bottom panel, it's similar to the second panel, but here the green is the diamagnetic current carried by ions, and the blue is diamagnetic current carried by electrons. So it is ions that predominantly contribute to the diamagnetic current. Okay, so we have talked about the structure of the magnetopause, specifically the location and shape, motion, thickness, and electric current. Now let's start talking about the dynamics of the magnetopause. I will spend most of my time talking about magnetic reconnection just because how important it is in the solar wind magnetosphere coupling. I will talk about its signatures and some outstanding questions. Magnetic reconnection is very important because it is responsible for the dominant transport of plasma and momentum across the magnetopause. Although all of us probably know reconnection from the cartoon illustration, in history, it was not an easy task to understand the smoking gun signatures of reconnection in observational data. And that's part of the reason why many people at early times were unsure whether reconnection happens or not. Here I will review some of the most commonly used signatures, and because of the large structural consequences of reconnection, reconnection can be sensed from large distances from the X-line, even in the ionosphere. So I will break down the signatures according to where they are observed. Okay, first at the magnetopause. As the magnetosheath and the magnetospheric field are interconnected, the magnetopause has a finite magnetic field moment, a component normal to the boundary. This boundary now can be seen as a compound structure with the rotational discontinuity as its major ingredient. For any discontinuity, the Rankine-Hugnoid condition provides a set of relations describing how the plasma changes across a discontinuity. And specifically for rotational discontinuity, the relation describing how the velocity change across rotational discontinuity is called the Wallin relation. So therefore, if reconnection is happening, the magnetopause should have a rotational discontinuity, and therefore the spacecraft measurements should agree with the Wallen relation. An example is shown on the right. It is a slightly complicated event because the spacecraft entered the Magnetopause multiple times, as you can see from the multiple rotations in the magnetic field data. But nevertheless, from the following two panels, we can see that the high-speed plasma jets were observed at all Magnetopause crossings. And here, the black curve is the observation, and the red is the predicted plasma velocity according to Wallen relation or Rankine-Hugenoid relation. And an excellent agreement can be seen, so that this observation suggests that reconnection was active during these crossings. The plasma jet is a fluid signature of reconnection, and if your target is to understand how magnetic field lines break and reconnect, you need to look at the immediate vicinity of the X-line where MHD breaks down or kinetic physics dominates, and that is the diffusion region. Given how small diffusion region is and how rapid Magnetopause oscillates, we've learned that that's several tenths of kilometer per second. Only the high time cadence of MMS allow resolving the electron diffusion region. The specific set of criteria that signify a diffusion region is still under development, but this study presents many representative features of this region. On the right shows the path of MMS, which traverse the plasma jets on both sides of the X-line, and it passed the diffusion region in between. So this diffusion region can be seen as the reversal of ion jets, which can be seen from this blue curve at the top panel on the left. So at the reversal, which is the diffusion region or dissipation region, however you want to call it, we see fast electron jets. Note that ions here are stagnant, but electrons are moving really fast. And then we have electric current, strong heating of electrons, and a large amplitude of electric field. Note that encounter of diffusion region is very rare. I think it's less than 1%. And on the other hand, magnetic reconnection is believed to occur almost all the time, just somewhere at the Magnetopause. And that's why, although MMS can resolve the diffusion region, we still extensively use the other signatures of reconnection to study reconnection. So we shouldn't abandon those techniques or tools. When reconnection is time varying, by the way, it often is, it produces magnetic ropes or tubes called flux transfer events. So the flux transfer event is another signature of reconnection at the Magnetopause. FTEs can travel long distances away from the reconnection site, and some evidence suggests that they can even travel all the way to the magnetotail. So FTEs can be identified as a bipolar variation in the magnetic field normal to the Magnetopause, enhancement in the magnetic field strengths, and a mixing of plasma from either side of the Magnetopause. And here shows the first ever observation of FTE by Rosso and Elphick. The magnetic field is shown in the boundary normal coordinates, where N, which is can be seen here, it's outward along the normal, the boundary normal, and L is my cursor here. L it's the projection of GSM Z direction. So two FTEs can be seen here, characterized by bipolar variation of magnetic field and enhancement of the total field strengths. Okay, now let's move to mid-altitude. So once the field lines are open, magnetosheath ions can enter the main sphere. These ions on one hand would move along magnetic field lines towards the Earth, and on the other hand, convect anti-sunward with the field lines. This means that particles with larger parallel velocity would arrive closer to the open-closed field line boundary, while particles with smaller parallel velocity would arrive at successfully higher latitudes. And therefore, if you have a spacecraft that cross the cusp from day side to night side, you will see a distinctive dispersion profile with decreasing energy with time and latitude. If reconnection is steady, then you will just see a single and a smooth dispersion, ion dispersion. On the right shows a different scenario where there are stepped ion dispersions. There might be two major steps, but there can also be smaller or minor steps embedded in between. This indicates that reconnection process is either occurring at spatially discontinuous patches or is proceeding at a time-varying rate. With single spacecraft measurements, we are unable to separate the spatial temporal effect, but hopefully with two spacecraft, for example, those from the upcoming TRACER mission, we can resolve this time and space ambiguity. Now, moving down to low altitude, or within the ionosphere. As magnetic field lines are equipotential, reconnection electric field along X-line can be mapped to the ionosphere, and it drives the ionospheric plasma to move. This would be seen as anti-sunward flow moving across open-closed field line boundary as shown on the left. This is a polar plot where we are looking down at the northern hemisphere from space, and the dayside aurora oval, which is this gray band, is shown. And the colors here represent the plasma convection velocity measured by a radar, and the red and orange just means the flow is moving at high speed in the anti-sunward direction. So this fast ionospheric flow is an ionospheric signature of reconnection. Besides electric field mapping, precipitation associated with reconnection produce a special type of aurora form, which is called the polarward moving aurora form. And as indicated by the name, these auroras are first appear in the dayside aurora oval and move polarward, and eventually become detached from the main aurora oval as highlighted here. And this polarward motion is consistent with the reconnected flux tube propagating towards the magnetotail. Okay, PMAFs are mostly produced by precipitation of electrons. Precipitation of protons generates a reconnection-associated proton aurora. These protons come from the magnetal sheaths and can leak through or can also be accelerated through the magnetopause thanks to reconnection. As they precipitate, they produce an aurora spot in the proton emission band, as shown here. Okay, now knowing all the signatures of reconnection, let's talk about three of the outstanding questions of magnetopause reconnection. Here, the questions address the macroscopic properties of reconnection. Kinetic physics is interesting, but it's not included due to the time constraint. But I would recommend you to take a look at MMS publication for that information. But firstly, one question is reconnection intrinsically intermittent, continuous, or quasi-steady? So here, intermittent means reconnection turns on and off. Continuous means reconnection may operate at a variable rate, but never cease. Quasi-steady means that fluctuation of reconnection rate, if present, it's a small fraction of the average rate. And also here, the word intrinsic means that without the disruption of solar wind, because if there are frequent changes in the solar wind, reconnection is not expected to be steady. So in other words, is reconnection intermittent even when the solar wind is perfectly stable? And by the way, solar flares and magnetospheric substorm, which are believed to be initiated by reconnection, have highly bursty occurrence. So this raises the possibility that reconnection is intermittent intrinsically. Interestingly, there are evidence suggesting that reconnection can be continuous or even steady at the Magnetopause. We have just seen these figures when talking about the signatures of reconnection. On the left, the spacecraft detected reconnection jets like these at all the crossings of the Magnetopause. So over this like 1 hour time or so, the spacecraft in total spent like more than half of its time at the Magnetopause, and reconnection flows were observed whenever the spacecraft were at the Magnetopause. So this is therefore interpreted that reconnection was continuous for over 1 hour or so. And in the middle, this single ion dispersion, as we talked about, implies that reconnection was steady. And here, this proton, this reconnection associated proton aurora spot is found to be present uninterruptedly for 4 hours, implying that reconnection was continuously active for 4 hours. There are also evidence suggesting that reconnection is intermittent. So FTE itself is a signature of time varying or presumably an intermittent reconnection. Cusp ion steps, as we mentioned a few slides before, imply that reconnection was intermittent if it was not spatially patchy, by the way. The ionospheric flow often exhibit pulsations in this kind of time series plot. So here the y-axis is distance from the radar and x-axis is time, color represent the velocity. And here we can see the velocity goes up and down at relatively high frequency. So therefore, both intermittent and continuous and even quasi-steady reconnection have been observed. So what is the dominant mode of reconnection and what controls the continuity or intermittency? Well, we don't know the answer. A second question is about the structure of reconnection in the direction normal to the reconnection plane. For southward IMF, this is the local time direction. So whether reconnection X-line is spatially extended or patchy, and what controls the extent are open questions. This figure summarizes some of the existing reports of the extent of reconnection in the local time direction. It is almost astonishing to see such a wide range of extent, from a few tenths of Earth's radius to several tenths of Earth's radius. This slide presents evidence supporting that reconnection is extended. In this GSM XY plane, geotail was located around the subsolar point, and wind across the I think this is the dawn flank. And geotail observed bidirectional jets, and wind observed northwards jets. Such simultaneous observation of reconnection jets suggests that the X-line has spanned the entire dayside Magnetopause from the subsolar point all the way to wind, if not further beyond. But of course, this assumed that the X-line was spatially continuous between these two spacecraft, and this assumption still warrants further justification. From the ionospheric perspective, let's examine the ionospheric flow and PMAF, which is the poleward moving aurora form. on the right shows the ionospheric flow and aurora. And we are again looking down at the northern hemisphere from space. No one is to the top. The anti-sunward flow and the PMAF in total spent 7 hours in MLT. This suggests that reconnection was spatially extended. There are also evidence supporting patchy reconnection. So for example, in this GSM XY plane, two Themis spacecraft cross the Magnetopause with a separation of 4 Earths radius, something like that. Themis A observed a clear, large amplitude plasma jet. So that's a signature of reconnection at the Magnetopause. Themis D did not observe such a jet, and its velocity change was inconsistent with the Walden relation. So therefore, reconnection was not happening at Themis D. So reconnection proceeded either as spatially discontinuous patches or just a single patch. In this ionospheric study, both the ionospheric flow and the PMAF were localized in MLT. So here's the PMAF, here's the flow. And this is very different from what we've seen from the last slide. So what is the characteristic scale of reconnection? What makes reconnection extent so diverse? And what's the similarity between patchy and extended reconnection? All of these questions have not been answered. The third outstanding question is, does the global configuration of reconnection follow the component merging or anti-parallel merging? Anti-parallel merging or anti-parallel reconnection is easy to understand. It means reconnection occurs when the magnetic field lines are exactly anti-parallel. Component reconnection proceeds with a finite guide field, which is also a magnetic field along the x-line, a magnetic field component along the x-line. So that here only the anti-parallel components will reconnect. So our current understanding, reconnection can proceed with a guide field or as a component reconnection, maybe just at a slower rate than anti-parallel reconnection. So this question is really about whether anti-parallel reconnection dominates over component reconnection. So distinguishing between anti-parallel and component reconnection has been difficult because quite often we don't know where exactly reconnection on x-line is. For example, based on the direction of reconnection jets or the motion direction of FTE, we can infer in which direction reconnection is located relative to the spacecraft, but not how far reconnection is from the spacecraft. So one breakthrough is made by Tratner, where he managed to obtain the reconnection location by using the ion distribution functions at the cusp. So here's how it is done. Previously, we talked about how precipitation looks like at a mid-altitude spacecraft. But in reality, the spacecraft may observe a second population, which originates from the magnetosheath, but travel all the way to the ionosphere and be reflected back to space. So there is a mirrored population. And the two populations can be seen in this observation on the right. So the x-axis is the parallel velocity and the y-axis is flux. So there are several peaks in this flux measurement. Here it's a precipitating population. Here it's a mirrored population. And in this event, there's an additional population, which is the ion outflow. So remember, what we want here is the exact location of reconnection from the spacecraft, which is this distance, xr. And xr can be estimated from the velocities of these two populations as represented by VE and VM. So specifically, the time it takes for the precipitating particles to reach the spacecraft which is the left-hand side of this equation, should equal the time it takes for those mirrored population, which propagate all the way to the ionosphere and back to spacecraft. So that's the right-hand side of this equation. From here, this is the formula of XR, and since XM, VE, VM are all known quantities, we can know where the reconnection is located relative to the spacecraft. So with this information, now we can explore the shear angle between the magnetosheath and the magnetospheric field to see whether the field lines are anti-parallel at the x-line. The figures here are called magnetic shear angle plot. So where we are viewing the magnetosphere from the sun. So here everything is projected onto the xy plane, and this circle is the size of the magnetosphere at the terminator, where x equals 0. The colors here represent the shear angle. It varies from 0 to 180. So the red means high shear angle between the Earth field and the draped IMF. So red represents high shear with nearly anti-parallel magnetic field lines. The black squares are simply the inferred reconnection location from the previous slide. So if these black squares are located within the red color, then reconnection follows anti-parallel reconnection. If not, then that's component reconnection. So on the left, the black squares are indeed located within the red region. So the reconnection here proceeds as anti-parallel reconnection. But on the right, these squares come from some yellowish green color. So that means the shear, the field lines at these locations are not anti-parallel, but have a significant guide field. So the reconnection here proceeds as a component reconnection. Okay, so last but not least, let's talk about Kelvin-Helmholtz instability as another dynamics of the magnetopause. So although reconnection can account for plasma entry during southward IMF, there's no consensus as to the northward IMF. And the low latitude boundary layer is often much thicker during northward than southward IMF, implying a significant amount of plasma entry during northward IMF. High latitude reconnection can play a role. Kelvin-Helmholtz instability could also be the reason. This instability usually occurs along the flanks of the magnetopause, where the magnetosheath flow is fast relative to the stagnant plasma, stagnant magnetospheric plasma. So on the right shows how Kelvin-Helmholtz instability looks like in spacecraft data. In a simple sense, when you see periodic oscillations, it is likely to be Kelvin-Helmholtz instability. But yeah, we can see periodic oscillations occurred where the spacecraft observed the hot and tenuous magnetospheric plasma and relatively cold and dense magnetosheath plasma. And oscillations also occurred in velocity and magnetic field and total pressure. Because the spacecraft orbital velocity was so small, these these oscillations must have been caused by magnetopause surface waves. And from the wavelet spectra of the total pressure, we can see that the dominant power is located around this location, which correspond to about 100 seconds in wave periodicity. And this is consistent with the typical period for Kelvin-Helmholtz waves. As an ideal Kelvin-Helmholtz instability, there won't be much mass transport. The transport can only arise during the nonlinear stage when there are rolled up vortices, like shown in this cartoon. So when these vortices collapse or when reconnection initiate in these vortices, plasma can be transported from the magnetosheaths into the magnetosphere. So it is important to know whether the KH instability achieve or develop into these rolled up vortices. And a single spacecraft, usually it's not sufficient because it cannot differentiate these rolled up vortices from the single ripples. And instead, we need multiple spacecraft separated in a normal direction of the magnetopause. And one such observation is made by a cluster. In this time series plot, the top panel showed the density, which is color-coded in this color scale, and it's sorted by different cluster spacecraft, C1, C3, C4. And the Y direction, it's here, it's outward along the boundary normal in this coordinates. The two following panels shows the velocity and magnetic field perturbation from the average, and different spacecraft measurements are color-coded following the text here. Also shown are the predictions from a simulation of a nonlinear Kelvin-Helmholtz instability. And we can see there's an excellent agreement between observations and the simulations. And this observation therefore shows that the KH instability has developed to the nonlinear stage, and therefore transport of plasma by Kelvin-Helmholtz instability is possible. Following reconnection, let's briefly talk about open questions of Kelvin-Helmholtz instability. So the previous study confirms that the Kelvin-Helmholtz instability can develop into vortices, but we still don't know the history of this evolution. So how does a Kelvin-Helmholtz vortex evolve from burst to collapse? Evidence show that as vortex twists the magnetic field lines, reconnection can happen inside the vortex. So how is magnetic reconnection initiated within the Kelvin-Helmholtz vortex? And when we talk about the magnetopause structure, specific the thickness, we mentioned that there's a dawn-dusk asymmetry of the thickness. So is Kelvin-Helmholtz instability also dawn-dusk asymmetric? And of course, what's the relative contribution of Kelvin-Helmholtz instability versus magnetic reconnection to plasma entry for various solar wind conditions? Okay, here comes to the summary of this seminar. And these are all the points we have addressed. So the magnetopause is far from being well understood, despite the tremendous expansion of our observational capabilities in the past few decades. But fortunately, our capabilities will continue to expand, and we expect to acquire lots of new insights in the near future. One strategy I think that is important is that rather than use each data set individually, we should think of ways to coordinate different data sets or use different data sets as one distributed observatory. Although this presentation has mostly focused on observations, it should be mentioned that enormous progress has been made in simulations as well, either MHD or hybrid or kinetic or a combination of them. And some of these simulations can reproduce the observations amazingly well and have helped us to deepen the theoretical understanding. Okay, so that's all about my presentation, and I'm happy to take questions.
Thank you so much, Ying. That was a very clear talk. It was great listening to it. So we have right now about 7 questions. So I'll go through them one by one. But before that, I just wanted to note to everybody that next week's seminar will be on the oxygen at the Magnetopause, given by Stephen Fuselier. So please join us next week, same time. But all right, so back to questions. E.J. Lund and Richard Denton asks in slide 7, sorry, can you go to slide 7? Basically, the question is the magnetopause velocity in the figures here signed or unsigned? That is the distribution symmetric?
Symmetric around what?
So from what I understand is like, is it signed? Is it, is it just in one direction, the velocity, or is both directions just?
Oh, yeah, I think this is just the absolute, well, I should say this is the speed, not the velocity. So
okay.
It hasn't considered the direction, like moving outward or inward.
So do you think that that's symmetric in general, or could there be an asymmetry? The velocity distribution moving outward and moving inward?
I think that's a very great question, and I don't really know whether it would be asymmetric moving out and in. I personally not aware of any studies have carried out that, but I think that will be a very interesting topic to explore.
Yeah, my guess is that probably it's asymmetric because the pressures, anyway.
And they could be caused by different processes, or they could have different triggers. So I agree, there's a high chance for it to be asymmetric.
All right, so question 2 is by Martin Archer on slide 12 and 13. How often is magnetopause reconnection quasi-steady versus bursty or FTE like?
Again, I think that's a very important question, and I'm not aware of anyone carrying out that kind of analysis. And personally, one thing I think is important is to compare the kind of intermittency versus continuity from different data sets, because I personally feel even for the same events, depending on what data set you are looking at, you probably will arrive at different conclusions, whether or not conclusion, interpretations, whether you think reconnection is steady or it's time varying. But in short, yeah, I don't think there's any statistical quantification about this yet. And I think it's important to compare different data sets.
Yeah, all right. So question 3, Jason Durr asks, can you comment on the left-hand side equation on slide 23 and how the distribution function is used to obtain that equation?
So the left hand of this equation, actually, it's just, it's not dependent on the observation. It should be universally valid. So it just describes how particles, so for the precipitating particle, it travels, it only travels this XR distance when it arrives at the spacecraft, but the mirrored particle, it travels this field line all the way to the main ionosphere and reflected back. So this is not dependent on the observation. But what is dependent on the observation is the specific value of the mirrored particle velocity, which is taken from this Gaussian fitting, and also this precipitating particle of this precipitating velocity, and that's this population. And also XM, it's the distance between the spacecraft to the ionosphere. And since we know where the spacecraft is, so XM, it's also known. So therefore, this relation is not derived from observation, but these quantities are do come from these observations. And from that, we can just simply know the XR.
Okay. All right. So question 4 by Zubair Shaikh on slide 23 itself. how can we know if the observed ion population is mirrored or coming from other sources?
So I think first you should have a velocity that's moving upward into space. So that's criteria one. And second, I think this population should have the energy should be on the order of mantle sheath ion energy. So for example, if we compare this mirrored population and ion outflow, the mirrored population should be more energetic than ion outflow because the ionosphere energy it's very low, but mantle sheath compared with ionosphere is hot. So I would say these two criteria.
Great. Question 5. David Seibeck asks, does reconnection of the magnetopause begin at a point and spread? If so, how?
I believe so. I don't know others, whether others believe so. But whether it's a point or it's a finite width, it's I think that has been beyond some of the instrument capability, but at least according to some of the observations made by me, we find that reconnection often starts from a localized extent and then grows. And another interesting question is what control its growth time? You know, how does reconnection know it should stop there without further growing? That's an interesting question.
Yeah, is it understood through the physics, like say the extent of spread?
Yes, so this is an area of simulations that is more advanced than observation. I think for more than 1 decade, simulation have shown that once you initiate reconnection from a point, it will spread. The spread could be due to could be carried by those electrons and ions, you know, as they move or as they carry the current, or it can be due to alpha waves.
Okay, so question 6, Elizaveta and Antonova, she asks, you consider the reconnection and Kelvin-Helmholtz instability on the magnetopause as the dominant mechanisms of plasma penetration through the magnetopause. Do you have any comments on the roles of other mechanisms, for example, finite Larmor radius effect and so on?
I think besides reconnection and Kelvin-Helmholtz instability, another often like mentioned mechanism is kind of like diffusion. So when you look at the wave, so when you look at the electric and magnetic field, high frequency measurements, there are often waves present in these in the boundary. So these waves can create kind of wave like scattering or diffusion that cause particles to diffuse from one side to the other. But I think that's an area that hasn't been, I mean, there have been some studies um, in that area and some very important progress, but I don't think we have fully understand that mechanism or have a fair assessment of how important that mechanism is.
Thank you. So question 7, again by Martin Archer. What controls the typical period of Kelvin-Helmholtz waves or vortices, and how variable is this?
Great question. I'm not an expert of how Kelvin-Helmholtz instability, so I actually don't know the answer in this area. But I think, yes, simulations must have their own like understanding of the wavelengths. And also, I think as far as I recall, the magnetopause boundary thickness also may affect the wavelet. But yeah, I would recommend you to unfortunately read some papers, for example, by this author and some theoretical simulations. Sorry.
Yeah, no problems at all. And if anybody else has comments on this, they can send the comments to us and we can put it up on the website. So The next one is from Chung Hu. The question is regarding the spatial extent of X lines. I wonder whether a quantification of reconnected magnetic flux would help infer that. Any comments on this?
Yes, so there have been studies using, I assume you were thinking about FTE to see whether reconnection, the extent of reconnection. So that actually suffer from the same limitation of like the satellite measurements. So for example, when you have multiple spacecraft observing the FTE at the same time, although you are seeing them at the same time, it does not necessarily mean they belong to the same flux tube. There could be multiple flux tube, happen to travel across the magnetopause at different local times. So therefore, so one way I would recommend is again just to combine different data sets. For example, combine the Magnetosphere data set with the Ionosphere data set, because in Ionosphere you can see the flow or the aurora in 2 dimensions. So you can see whether these are, kind of like a string of different FTEs or it's just one continuous FTE.
So you're saying from that we can infer something about the spatial extent of the X line?
Yes.
Okay. All right. So the next question is from Louis Precer. Am I pronouncing it wrong? But what is, in your opinion, the necessary signatures that have to be shown by a spacecraft in order to say that it is observing reconnection, besides the fast bulk flow? I think.
So usually the common way to identify reconnection events is to use a combination of fast flow and also, this is something I didn't mention in this talk, it's called the D-shaped ion distribution. So that it has a D shape mostly because only part of the magnetosheath particles that moving towards the magnetosphere can enter the magnetosphere. So this is the common way of identifying reconnection. And if you are interested in reading papers, you may find this is the commonly, this is the powerful combination in many statistical or even case studies. So I would say, yeah, the fast jet, it's something, I would say it's a very important criteria that everyone should consider to use. But of course, if you are, let's say, very far away from the X line, the flow may have been slowed down, not accelerated, then you should see the FTE. That's an alternative signature.
Seth Dorfman asks, does the equation on slide 23 take into account that the particles will slow down as they mirror? That is, Vm is not constant over the particle path. If not, how big of a correction will this be?
I don't think I don't think this has considered the time varying velocity along as particles travel along the field lines. So I think this will be one uncertainty factor, although actually if you think about this, there are several uncertainty factors, including how you determine the velocity. And in fact, in order to know where reconnection exactly happened, you need to have a field line model, just like these orange lines assume. So I would say I think the author also comment on the uncertainty or the performance of this method. And it could be the uncertainty or the uncertainty range can be a few Earth radius, maybe on the low end of the few Earth radius. So it's not a perfectly precise characterization, but has definitely been much improved from what we know before.
Got it. So the last question, Primoz Kajdik asks, is steady versus patchy reconnection related to the variations of IMF orientations in the magnetosheath?
I think so. Oh no, I think that's a possibility. So even within, let's say, the intermittent reconnection community, there are two, I would say, different types of opinion. One is that reconnection has its intrinsic time scale of intermittency. So that's often found to be like a few minutes. And other studies just seem to support that, that's not really a favored frequency. It's just happened to be a power law distribution and it has a peak there. So therefore, I would say currently there are two different opinions regarding what controls the intermittency, whether it is just is determined by reconnection physics, or it could be triggered by external variations.
Yeah. Okay, so that was a great question and answer session. Thank you for answering everything, Ying. So if there is no more questions, I think we can call it a day. And thanks a lot for coming in and giving this talking.
Yes, thanks, Ying. We'll see everyone next week, hopefully, with Stephen Fuselay's talk on oxygen at the magnetopause and outside the magnetosphere. Thank you, everyone. Have a good week.
All right.
Thank you.